Hello again, geology enthusiast. Here we are back for part 2 of absolute time, my dating techniques. So what we figured out is that absolute time helps us to assign ages to things in our environment. And we're going to continue our discussion on that. So on the screen, I just have a little bit of a review. Isotopic dating sometimes can prove a little bit challenging, so I think review is good to get us all caught up on the same page. So the purpose of isotopic dating is to look at isotopes of elements that are not stable. Not all elements on the periodic table are isotopes, but some are, and it is those isotopes that go through decay processes in order to reach stability is the ones that we look at for isotopic dating techniques. And so when we're talking about an isotope, we're thinking in terms of its decay over an exponential time period. And that makes sense. So early on in the semester, we talked about the difference between linear and nonlinear rates, and if we see them in nature, and we said that you don't usually see a linear rate, but in fact, you often see nonlinear rates. And so this is just another example of that. So it's that instability that's helping us to use it as an indicator of time. Looking back at the periodic table of elements and defining an isotope, atoms that have the same number of protons. So remember that when we look at the periodic table of elements, it is organized by atomic number and atomic weight, and those increase from right to left. Right to left. I think that's right. They increase over time. So hydrogen has an atomic number of 1, helium has atomic number of 2, lithium has atomic number of 3, etc. And you can see that on your periodic table. So with isotopes, we're interested in asking the question if they're gaining or losing neutrons. And we use an instrument called the mass spectrometer in order to weigh those differences. So we're able to actually weigh the mass of an atom to tell if it's increasing or decreasing over time. And then with that, we have to establish something that's called a half-life. And so there are, and how do we do that, right? That's usually what questions students ask me, like, well, how do you know that it's that is the half-life of an isotope? And so we use isotopes that we can measure throughout their entire decay period. So something like helium, tritium, deuterium, rather, so H2H3, it goes through a decay process of 13 days. So we can measure its entire decay process. And when we do that, it measures exponentially. And then we make sure that these things are testable and repeatable as we look at other isotopes. And I'm going to show you today about how one of those scenarios were challenged and what the scientific community did to fix it. So in the last episode, we talked about uranium-238 as an isotope. It has 92 protons, 146 neutrons, to equal 238. So the number of protons and neutrons together add up to the atomic weight. So that should be no surprise when you come to the next exam. So I should be able to give you any type of isotope, assuming you have the atomic number and atomic weight, and you should be able to come up with the decay process. You will remember, based on our definition, a half-life is the time required for 50% of the atoms of a radioactive isotope to decay to its products. And that's the decay chart that you see on the right, which is exponential. So we talk in terms of half-lives, and then we assign years to those half-lives. And we've done that for a very common indicator that's called carbon-14. So we mentioned carbon-12 is found on the periodic table of elements. Carbon-14 is an isotope of that. And we said that carbon-14 originates in the atmosphere. The carbon dioxide that's in the atmosphere is carbon-14. So carbon-14 is in the atmosphere. Plants ingest it through the process of carbon photosynthesis. People eat the plants. People eat the meat that eats the plants, the animals that eat the plants, and then we ingest it through our lives. So everything that is living or organic is ingesting carbon-14 throughout its entire life cycle. And then the moment that the person, animal, or plant dies, that's when the decay process starts. So because we're continually ingesting it through our lives, we're assuming that the parent has 100% of that product and the daughter has 0%. So that there's 0% nitrogen-14 in our body until we start to go through the decay process. We talked about the different things that can be carbon dated. So anything that's organic can be carbon dated up to 50,000 years. So the maximum span of which carbon-14 dating can be used is 50,000 years. And that's because you have to have a ratio of carbon to nitrogen-14, or you have to have a relationship between the parent and daughter product. So you're not losing mass, you're just switching mass between the two. So you have 100% carbon-14, you have 0% nitrogen-14. After one half-life, you have 50% carbon-14, 50% nitrogen-14. After 3 half-lives, you have 25% carbon-14 and 75% nitrogen-14. And so what I need to communicate is that those 3 parts of the decay chart are always consistent. So because it's based on what an isotope is. So you're always losing 50% of that parent product, and it's always being added to the daughter product up till it reaches 100%. What does change on the decay chart is the half-life, and I have to give you the half-life. That's not something that at the 101, 102 level that you calculate, but I will give you that value. And then that's just a matter of adding the numbers sequentially. So what I want to talk today about is talking about the scientific method and the beauty of that, and the real revolutionary ideas that came out of being able to absolutely date rocks. So remember, the geologic timetable was first invented in the mid-1800s, and it was just based on relative time. So looking at sequences. It wasn't until 1950 when the mass spectrometer was invented that things could be carbon dated. So radiometric dating or carbon dating was the very first process that took place. And so a fellow by the name of Libby established this process. He won many prizes for it because it changed not just geology, but it really revolutionized anthropology and sociology, as you can imagine, because now you can go to a museum and date a textile or a painting. And so especially modern Earth history, world history really came to life if we want to know about civilizations, etc. So Libby in 1949 determines that carbon decays at a rate of 5,568 years, plus or minus. Now this is different than the value I've been giving you. I've been giving you a half-life of 5,730. But when in 1949 carbon dating was first established, the rate at which Libby presented was 5,568 years with an error of plus or minus 30 years. So as the story goes, we move forward in time, and a fellow by the name of De Vries came along, and he was an anthropologist. So he was studying ancient civilizations, and he was so excited about using carbon-14 dating techniques. So he used it on a variety of different types of textiles and potteries and linens. And what he realized was the dates that he was receiving back from the mass spectrometer were not accurate according to what he thought those civilizations could be. So he went back to Libby and said, Libby, I don't think your dates are correct. I think you need to to check on this. I think something's going wrong. And what was established that the amount of carbon-14 in the atmosphere has not remained, nor does it remain, consistent over geologic time. So there's some atmospheric fluctuations that happen. And so the problem is that if that's fluctuating, then the rate at which it's being absorbed is also going to fluctuate. So the half-life established by Libby of 5,568 was incorrect, ultimately. So then the question became, how are we going to solve this? And this is where we tie it back in to our discussions of physical counting methods and natural indicators of absolute time. So we talked about dendrochronology and the beauty of using tree rings. So what we said was, you know, you can plant a tree in your yard, you come back 25 years later, the tree's still there, it's growing an annual growth band every year. You have confidence that that tree is 25 years old. With dendrochronology, we can, because of sensitivity and complacency, we can map up and link up the story of those tree rings. And that's really what this little diagram schematic is showing you. So if you have an entire forest, or if you have an ancient forest, so remember that trees can be petrified, they preserve those tree rings still. So you can overlap them to extend the story. And so what Libby decided to do was to look at that tree ring data and to extend it back. And so he looked at the dendrochronology of bristlecone pines in the United States, German oaks, and Irish oaks. And he linked that story back about 10,000 years, so to the very beginning of the Holocene epoch. And you can do that confidently, right? Because you know how old the tree is because you've counted the ages. You know that they respond to climate changes, so you can look for those patterns in the natural environment. So they established what's called a radiocarbon calibration curve, whereby they use tree ring data that gets them back to about 12,000 years, and then they go to the coral record. So corals extend it to about 20,000 years. And again, this is a small snippet of geologic history, but remember, carbon dating only goes back to about 50,000 years at maximum. So you take your tree rings and you take a tree that you know is 100 years old, and then you take that sample and you put it into the mass spectrometer. So the age of that you receive from that mass spectrometer better be 100 years old. You take a piece of coral that you're confident is 1,000 years old, the mass spectrometer better turn out a date that represents 1,000 years. And so this is called the radiocarbon calibration curve that's based on physical counting methods. So it acts as a check and balance. So we can look at the diagram on the screen, and you can notice the linear line, so the line that's straight, and then you can notice a line that wavers away from it. So the line that's straight is the calibration curve. So that gives you a specific point in time based on the amount of carbon-14 you expect to be in a sample and how old it is. The wavering line is just an example that that this type of dating technique, any type of dating technique, has air to it. And the older the sample is, the more air is going to be. So in this case, the further that you get away from modern, the more air is introduced. And so that's why when we talk about age dating, we always say plus or minus. And we recognize in the world of geology, as we established like the very first day of class, that you know, geologic time is expansive, right? And so you're expecting, if you date something, that there's going to be some type of error, but we're really most of the time just trying to get into the ballpark. So if we say something is plus or minus 1 or 2 million years, it's relative in the grand scheme of geologic time. So by doing that radiocarbon calibration curve and going through that revision process, which is a beautiful thing, mind you, because that's what the scientific method is, right? So you publish, you're a scientist, you go through a peer review, people agree with you, you publish your data, and then people still have the opportunity to challenge your data. So things don't become a theory without being challenged and accepted into the scientific community. So this is an example of that. Somebody saw an error, it went and was revised by the radiocarbon calibration curve. So at the end of all of this, by about 1960, there comes something that's called the Cambridge half-life. And the Cambridge half-life is the revised date of 5,730 years. And that's based on the calibration curve. And what it says is that Libby age was about 3% too low. Another thing I should mention here is that early in the semester too, we talked about overcoming geological boundaries. And so this is one of those instances where we overcome a geologic boundary. So it wasn't until the mass spectrometer was invented that we were able to absolutely date things in our natural environment. So we were able to overcome a technological boundary that really pushed our science forward. Some say it's one of the most revolutionary things that have happened in geology to date. So so 5,730 years is the Cambridge half-life. I refer us back to the calibration curve because I want you to ask the question, what is the term, what does the dating term before present mean? Because I'm sure that you've seen that, like even if you're a non-scientist, you've heard of before present if you've been to any type of museum. And before present refers to the year of 1950. So remember that Libby introduced this in 1948. He introduced the radiometric dating technique in 1950. And so once they were revising and making the radiocarbon calibration curve, they had to go back and figure out how much carbon-14 was in the atmosphere, and they were able to do that by 1950. So they began to monitor that, so that becomes the standard reference point. So before present is 1950. And that becomes more important if you're interested like in modern history, modern civilization, sociology, anthropology, because anytime you're dating something, you have to know what your reference point is. So your reference value is not 2020, your reference value is 1950 when they say before present. This is mostly for the science majors. So for the environmental science and then my geology students, I want you to take note of two different terms. First one is conventional C14 age, and the second is the C14 calibrated age. The difference between the two is the conventional C14 age could be reported in a scientific paper, and that is usually in a paper where carbon-14 was just started to be used. So it's kind of like when the Libby half-life just came out, this dating technique just came out. So those dates were obtained before the carbon calibration curve was revisited. So those dates were obtained on samples before 1958. And that's important because there's a lot of like foundational concepts, because it was like a big boom in 1948 when this dating technique came out. Everybody wanted to use it. So there's a lot of things in history that have been dated incorrectly, essentially, because remember the age is about 3% too low. So then if you're reading a paper and it says conventional carbon-14 ages, that means that the dates have not been revised. If it says C14 calibrated age, it means that they have been revised. Another thing I need to reiterate when talking about these dating techniques, remember that carbon-14 or radiometric dating can only be used for things that contain carbon. Okay, so the majority of samples on the planet do not contain carbon and are older than 50,000 years old. So we have to look to other isotopes in order to date them. So when we are looking to date a rock, we are not using carbon-14 dating. Do you get it? So you have a piece of sandstone. The sandstone is made of what? Quartz pieces of sediment, right? SiO2. Does it contain carbon? No, it doesn't contain carbon unless it contains like a piece of petrified wood or a shell. So there's some exceptions. But generally, if you find a piece of sandstone, it's going to be much older than 50,000 years. So it's not something that we use to date rocks or date the age of the earth. So we need to get our minds around that because it's a big misconception. So when we do try to date the age of the earth, we use the decay process of uranium. And it's called the uranium disequilibrium series. So we said that uranium-238 is on the periodic table, and we said that isotopes all want to decay to stability. So uranium-238 wants to decay to lead-206. And this complete decay process is happening over 4.6 billion years old. So some of the oldest rocks on the planet, and remember, there's not a lot because of what? Plate tectonics and Pangea cycles. They destroy the original bedrock, but we do see signatures of it in Greenland, in the Upper Peninsula of Michigan, and in Australia. So we do have samples. So uranium, the cool thing about uranium-238 decaying to lead-206 is that it's called the disequilibrium series because we can tease out different parts of the decay series. So it doesn't just go from, it's not as simple as carbon-14 decaying to nitrogen-14. That's a one-step process. With uranium, there's many processes that are involved over such a long length of time, right? So here's an example, and by no means do you have to memorize this chart, but I just really want you to know that this can be a tool for dating things like in the Quaternary or other aspects of geologic time. So uranium will first decay to thorium-234. Thorium will decay to protactinium-234. Protactinium decays to uranium-234. Uranium-234 decays to thorium-234. So each of these individual isotopes has their own set of half-lives. So we can pick these out and we can look for these signatures in different types of rocks, in different types of coral environments. So it's just very useful to have an understanding that there are many different dating techniques that we are able to use as geologists. And oftentimes, because we do want to be confident in our dates, we pick two different sets of isotopes. So like if you have a piece of granite, which you now know is made out of potassium feldspar, biotite, and quartz, so three different minerals, so they have different mineralogy that contains elements, we can pull out two different sets of isotopes. So we might pull out on our chart, maybe it has lead decaying to bismuth, depending on how old it is, and then we would overlap that with bismuth decaying to polonium, right? And so you run your mass spectrometer for both of those samples to give you a date that overlaps. And that's just to ensure our confidence. If you're interested in any of this or all of this, especially as it relates to climate change, I teach a class called Cenozoic Global Climate Change in the spring. And I would love to have you as part of that. This just more simply pulls out those different dating techniques and shows you the length of time that they are. And again, like some of them are so short that they're able to be measured at modern day. And so that gives us confidence in isotopic dating techniques because we can measure it through its entire decay process. Okay, so you're going to need to write all of these down, and you're going to see this on your first exam in some capacity, I promise. In the world of isotopic dating techniques, we have to make some assumptions. Okay, the first assumption is there is no daughter product present at time of creation. Only parent product is deposited. Sorry about that. No daughter product is present at time of creation. Only parent product is deposited. So remember from that last lecture where we made the decay chart, and we started with 100% parent and 0% daughter product. Oh, can you see that? 100% parent and 0% daughter product. That's what this is getting to. So we have to make an assumption that there's 100% parent product and 0% daughter product because we're making a ratio, right? So if there's any portion of daughter product originally there, it's going to throw off your date completely. So it's an assumption, and that's often why we look for two different types of isotopes to make sure that we correct for all of these assumptions. The second, sample has not been altered since deposition, no exposure to extreme heat, pressure, or weathering. Oh no, that's our whole rock cycle, isn't it? Wonder what we're going to do about that. The sample has not been altered since deposition, no exposure to extreme heat, pressure, or weathering. Yeah, so that describes what? Metamorphic rocks and sedimentary rocks. Great, fantastic. We'll come back to that. Third assumption. Rates of decay are not constant. Rates of decay occur in an exponential rate. So that's our assumption when we talk about the decay of an isotope, right? 50% parent goes to 50% product over one half-life. The good news is we know that no rates in nature are linear. And the other good thing is that we can test it. So we can show how there is exponential decay. And not just with something that has a short half-life, but if we have, if you have something with carbon in it, you can look for the percentage of carbon versus the percentage of nitrogen, and it's going to show you that decay curve over any portion of its decay process. And the last one is there must be sufficient amounts of parent to daughter isotopes to be measured by the mass spectrometer. So this goes back to that idea that we only use carbon-14 or any isotope to about 8 half-lives. Because once you're approaching 9 half-lives, you've got such little amounts of parent product left that you can't make the ratio. And remember that the older the sample is, the more error is assumed. And so really you really after if you only have 5% of that parent product left, you really don't want to get a date beyond that unless you have to. And if you do, you're making a pretty big assumption. So you have to have sufficient amounts of parent to daughter isotope to measure it. So those are our 4 assumptions. Let's ask some questions about those. Based on the assumption, which rock type would produce the most accurate isotopic date? And we've kind of hinted to this already in class when we started talking about the formation of igneous rocks, haven't we? So when we talked about igneous rocks, we said that those that are aphanitic or glassy are exiting the Earth's surface, most likely in the form of a volcano. And when they hit the atmosphere, they're cooling quickly. And so as they cool quickly, those minerals within it are solidifying quickly. And so when we talk about those types of rocks that have the most accurate isotopic dates that are the best for establishing an age, they're for sure going to be extrusive igneous rocks. So you're thinking in terms of basalt and rhyolite, obsidian. Like that's like the smoking gun. That's what you're looking for. And that's because they're instantly trapping the signature and the mineralogy is solidifying, which means your isotopes are being locked into place. And then the decay process starts. So, fine, that works out great. Now we can ask the alternate question. I'm not going to put this up yet because you'll see the answer. The alternate question is, which rock type would produce the least accurate isotopic date? Which rock type would produce the least accurate isotopic date? So that leaves you sedimentary rocks and metamorphic rocks. But our challenge is, based on our assumptions, it said sample has not been altered since deposition, no exposure to extreme heat, weathering, or pressure. Okay, so let's tease this out. Which rock type would produce the least accurate isotopic date? On the screen, we're going to lead you to sedimentary rocks that produce the worst results. Riddle me this. Okay, so you know that a sedimentary rock that's clastic is the accumulation of grains. So we're thinking in terms of sandstone. So sandstone that represents a beach environment has individual grains of sand made out of quartz, SiO2, that have been lithified together. For sure, you can individually date those grains, but if you do that, the date that you arrive at is not the date of formation of that igneous rock, of that sedimentary rock. It is the age of the individual grains. Are you following me? So you can date a sedimentary rock and you can come up with an age, but it's not the age of lithification, it's the age of the sediment. And so that might be useful if you're trying to figure out where the sediment came from in the environment. So where that original rock was that provided the source material for that sedimentary rock, but it's not going to tell you the age of sedimentation. There's other ways to figure that out. There are different dating techniques that's called optically stimulated luminescence dating, where you're dating the last time those sands of grain absorb sunlight. So that's really useful in figuring out the age of lithification. And we use that when we talk about like the age and evolution of barrier islands, or the formation of beaches, etc. So you can use isotopic dating to date a sedimentary rock, but it's not going to tell you the age. Next, we're going to talk about metamorphic rocks. So by the process of metamorphism, you're adding heat and or pressure. And that was one of our assumptions, that the sample cannot be exposed to heat or pressure after deposition. So with a metamorphic rock, you can use isotopes to date the metamorphic rock, but you're not getting the age of the rock, you're getting the age of when it last underwent metamorphism. So remember, when we talk about metamorphic rocks, you have a protolith, and so your protolith is your parent rock. So let's just say you have a piece of shale, You add heat, you add pressure, it turns into slate. Slate is the metamorphic variety of shale. And so you can date the slate, but the date that you're going to arrive is going to be much younger than what that actual shale is. It's going to give you the time that it underwent heat and pressure. So the good news is, if you're trying to understand mountain building, for example, if you want to understand when was the Appalachian Mountains formed, then you would look for those metamorphic schists in the Blue Ridge. You would date those, and the date comes back to be about 300 million years. And in fact, that was our last Pangea cycle. So it's useful, you can do it, but anytime that you have a protolith and you add heat and pressure, you restart the dating clock and the decay clock, essentially. So the ages come back much younger. So dating techniques are pretty fascinating. We're going to play around with them quite a bit, and I want you to get your mind around the idea of the decay chart and be comfortable with that enough to be successful on your exam. So I think I'm going to stop here for today. You've been a wonderful audience, and I will see you soon.